Okay, hello everyone. I'm going to talk about our work on proactive transparency in software update systems. So to start with, why do we need software updates at all? So back in the time of first digital computers, the programs as we now know them now were essentially just paper tapes with holes punched in them. And sometimes holes were punched erroneously, and to avoid the costs of producing entirely new tapes, the tapes were updated simply by patching small pieces of a tape on erroneous holes. And it's widely believed actually that the term computer patching comes from this process. So nowadays updates are a little more complex than a piece of a tape, and we use them to patch vulnerabilities, to fix bugs, and add features. And if you don't update your system, things can go wrong. And just 3 months ago, we saw outbursts of WannaCry, which used the vulnerability in Windows system leaked from NSI archives. And the thing is that Microsoft had issued an update for this vulnerability, but organizations and people just didn't apply them. But even if you do update your system, things can go wrong too. And the reason is that because software update systems by itself are a very lucrative target attack point, because just breaking into one system, you can infect hundreds of thousands of users. So the main question which we wanted to handle in this work is how can we make the software update systems more secure and transparent? I will start with showing how usual software release process looks like nowadays, and then identify 4 key challenges that we want to address to make it more secure. So usually there is a group of developers. It can be a company who writes source code, review it, and they have a master signing key. Either like all of them have access or only one person, which they use to authenticate releases. And the public counterpart, it is installed on users' machines, for example, during Bootstrap. So when the release is ready, the developers send it to a dedicated build server and get a binary out and sign it with a master signing key. And when the update is delivered through distribution center. So the first problem that we have is the master signing key is essentially a single point of failure. And if an attacker manages to compromise it, when he is able to create fake updates with a correct signature and just distribute it to end users. And this is not hypothetical. Just a month ago, we saw a burst of non-Petya attacks, and basically attackers or a group of attackers were able to inject malicious source code into a software update and infect thousands of machines in Ukraine and Russia and other countries. 3 days ago, we had a compromise of X manager or from company NetSarang, and it's also believed that software updates were involved. Flame malware, when in addition to hash collisions, there was a vulnerability with Windows updates. Then were PKI breaches and compromises the update servers themselves. And the second challenge is that the build server can be compromised too. And if attacker takes the build server over, he can just substitute a legitimate binary with a malicious version, and developers wouldn't even notice it and sign. So there's a partial solution to that, and it's called reproducible builds, which is a set of techniques for writing software so you can compile the same source code into the same binary each time, which is not the case by default, by the way. And Debian puts a lot of effort in that. But I actually would like to ask you how many of you have actually reproduced any software for personal use? 3 people. Well, this is not very surprising because, for example, to build Tor browser and all the dependencies, you need 32 hours on a laptop. And I tried to do it myself, and I never could finish. And this is also a solution for open source software. But what do we do with the closed source ones, which probably dominate the market nowadays? The third challenge is protecting users from targeted attacks. So assume there's some powerful unknown adversary who bribes or coerces developers who are, by the way, can be underfunded or just volunteers to create 2 versions of the update, where one has a backdoor and delivers a backdoor version only to one user. And currently there are no mechanisms that would allow this user to discover that he's being targeted. And The one example of that is a recent debate between FBI and Apple when FBI wanted Apple to sign a backdoor update to install on San Bernardino terrorist phone. And public were strongly against it because we didn't know if FBI would ever try to misuse this update in the future. And we don't know now if this situation will repeat again. And the fourth challenge is a somehow long-standing challenge in software development is how can we enable developers to securely rotate their keys. So if they just renew the key, so one approach now is just to create a key and sign it to the previous one. But if the key is compromised, attacker can do absolutely the same, and the users have no means to identify which of the keys is true key. So now it's time to show how we address these challenges with CHAINIAC. So I will start with a commonly used software release pipeline as a strawman design, and I will build CHAINIAC step by step by just addressing the challenges that I've shown you. As a first step to address the partial key compromise, we don't reinvent the wheel, and we just enlarge trust base by asking each developer or, for example, a team manager have individual signing key to validate releases. So in the beginning of the project, all the public keys will be placed in a policy file, and the policy file will be delivered to end users, as it's the case with public key now. So when the release is ready, the developers or teams review the source code and basically try to identify if this source code is the one that they intend to send. When they reproducibly build it using the reproducible build techniques into the binary and or binaries for different platforms, and if these binaries match the one from build server when they sign it with the individual keys, and when the release with the signatures is sent to end user. So this sounds good in practice, secure multiple signatures, but in reality we know that the end user wouldn't build the software, and user has to verify a multitude of signatures, and developers have to compile the source code each time. And if you work in security-related work, basically you may have to do it every day. So naturally, to solve this debate, one straightforward solution would be just to have a third party who would take everything for the developers and try verify and then vouch to end users, hey, I checked it, it's fine. But it would go against our approach because this third party would just retain all these 4 key challenges because it would be susceptible to all these problems. So to find this trade-off, the sweet trade-off between complete decentralization and a centralized third party, we rely on background work of collective authorities. So the idea of collective authority is that it's a group of servers who are only independent servers, who are only trusted as a group, but not individually. Basically, this group can collectively validate some statements. It can be timestamps or software updates in our case, and produce a single collective signature. And there is also a mechanism so that members can reach a consensus. Basically, BFT COSI is a consensus mechanism. So what we do, we introduce authority into our design now. And the members of the authority can be run by both. Ideally by some of the developers or the company, and by other tech companies or public institutes like EPFL. We're more than happy to do this. And now the policy file with the keys is installed on the authority members, and the user has only one single public collective key. So when release is ready, developers still validate the source code, but they don't compile it. They only take the version from a build server. And they sign it and send it to the authority. So authority now verifies all the signatures against the policy file and reproducibly compiles the source code. Each member does it independently. And if there's a match, they produce a single collective signature, which is releases when sent to the end user who can verify the signature. And we call this approach verified builds because in comparison to reproducible builds, where end user knows that in theory the binary that he gets or she gets is can be built from the source code. Here, the binary that user gets it has been verified to come from this very source code by multiple independent parties. And now a good thing about this approach that now companies with a closed source software can use it too by just signing NDA with the authority members and still provide assurance to the end users about the source to binary correspondence. So I was talking about the policy file and what should be there. As I mentioned, it should be a list of individual keys. It should be a signing threshold because we don't want them, for example, it's a team of 10 developers. We want something reasonable like 8 out of 10 signatures. So also it should be the authority collective public key, supported platforms for verified builds, and some other things too. So now, how can we address the challenge of protecting users from targeted attacks? Here again, we take somehow known approach of increasing transparency in the system and propose to have a authority-controlled transparency log of the releases in the form of a hash chain, basically when each new release includes a pointer to the previous one. And this is actually done by the developers who would now include the pointer to the previous head. And this would be verified by the authority, and if it's fine, the release would be appended to the hash chain. And now the user has, basically all the users are ensured to see the same view because authority would control that there is no two releases under the same version. And if there is a backdoor, it still stays in the public scrutiny, and at least all the users get the same, and you can't target someone. The final challenge is that so far we assume that developers just place their keys in the policy file in the beginning, authority gives the collective key to the user, and that's fine, it's forever. But in the real life, it's not the case. In real life, the developers leave and join, they rotate their keys. So how can we enable them to do so? So we simply propose to place the policy file, which if you remember includes the developer keys, into each release. And in this way, if, for example, even 2 keys are renewed or compromised, and if a threshold allows so, developers can create a new policy file and roll it out as a new release by signing with the previous keys. And if the authority would agree, it would just place it in the hash chain. But the next question is, it's good that we enable developers to rotate the keys, but it's not what users use to validate releases. Because users actually use a collective public key. And the authority membership can change even more rapidly because authority members have to change their keys more often. So what do? As I mentioned, we already place the authority public key in the releases, but now we don't really want the end user to go over each release in the transparency log and verify all the signatures. So we propose to have an upper layer of the authority configuration in the release log, such that the end users can go there and retrieve the latest public key and the latest membership. And this is basically what's used to sign the releases. And if one server changes, when the new block is created, which would point back to the previous. But there are 2 issues. First of all, how outdated user can, with outdated key, how can user be sure that the latest authority configuration is indeed a legitimate successor? Because if you know how hash chain works, basically you can make a lot of forks, and all of them would include the hash of the previous one. And second question is, how can we do it efficiently, especially if you're offline like for a year, and if the user is an IoT device, and we don't want them to verify like thousands of signatures. So to solve that, we propose a new data structure, which we call Skipchains. And the Skipchains is a data structure, blockchain-like data structure, loosely inspired by skip lists, and it has 2 features. And the first main feature is, in addition to backward links, which are also hashes, is in a traditional blockchain, we've introduced forward links, which are collective cryptographic signatures. Well, in our case, it's collective because we have a membership, but in, for example, permissioned setting, it can be just a signature. And the second feature is now that both backward links and forward links can be multi-hop. So you can search the timeline efficiently. And the forward links would allow you to traverse the timeline in the forward direction. So if you remember the user, he would be able to take his last block and see if there's a signature pointing forward, just traverse along it. So I'll show you how it works. Assume we have a yellow membership. Yeah, yellow membership here, and it's recorded in the skip block. And when at some time one of the members changes, and it turns into nice green membership. So the membership will be recorded again, and now it would include a pointer to the previous one in the form of the hash value. But in addition to that, the members of the yellow membership create a signature on the next green one and append it to the previous block, to the past. And this is somehow a forward link. And if the membership changes again, when it's again includes the backward links, but now they can be also multi-hop, so you can jump backward faster. And the same is with forward links. And so on, and we have the longest links between yellow and white membership. And so it's very useful, we believe, to have a forward links, but it creates somehow security caveat that the members, for example, of the yellow membership, they still have to store their private signing keys, even if they don't use them for signing releases. And to mitigate this risk, we propose two approaches. The first would be to limit the distance of the forward links, for example, to half a year to a year, which is already reasonable, because even if you want to jump for 100 years, you will just need to verify 100 signatures. And the second is what can be used. We haven't implemented yet, but that's a potential idea, is to use forward key derivation. So, for example, when the members sign something, they simply derive a new key from the previous one and erase the last one, so the attacker would not be able to compromise the previous forward links. So let me talk a little bit about implementation and evaluation. So CHAINIAC is implemented at Go. It's publicly available. You can already go and check it out on GitHub. And we use the Dedis crypto library of Go and on networking framework. If you would go to the Dedis user on GitHub, you will find the up-to-date implementation of the crypto library and the network and the Khoffi framework too. So regarding the evaluation, there was one question that we primarily wanted to answer. How costly is CHAINIAC? Can we really go to the companies and say, hey, here's a solution, you will be more secure? So for that, we have done a few experiments. I think the most interesting one is what's the CPU cost on the Khoffi nodes to validate releases. So if developers send you the releases and you need to do reproducible build, signing, and place it in transparency log. So for that, we took 6 Debian packages, like security critical ones, over 2 years from the history of Debian. And we choose Debian because they have reproducible builds, basically. And when we measured what it takes. So on the x-axis, you will see the size of the Khoffi. So the 3 is basically what's on the picture. 15 is slightly bigger, and when the 100. And the time on the y-axis. Basically, you can see that the reproducible builds or deterministic builds dominate the validation time. And the only 2 things that depend on the size of the Khoffi is collective signing and the creating timestamps, because you basically need to reverse a tree down and up. So the main takeaway from this is that if you just rent a simple server for $10 a month, you would be able to validate Debian security repository, which has a frequency of about 8 updates a day. Because basically, on average, it was taking 5 minutes to validate one release. So in addition to this, we did more experiments. I will not show you, but if you're interested, please go and read the paper. So we just evaluate how reproducible the reproducible packages are and how much time it takes. So we reproduce like 150 packages, random, security critical, and it took from 1.5 minutes to 30 minutes. What we're basically doing, we're taking Docker container, creating the recorded environment and building, and then comparing the hash. We evaluated the benefits of Skipchains, and we took real data from the Python package repository, and it helped us. It kind of allowed factor of 30 decrease in communication cost. And finally, we also had an idea of an aggregate layer of CHAINIAC, basically how to protect the whole repository of Debian, for example. And in short, the idea is to take snapshots of the repository from all the individual release log and create a tree and send it to the end users that want to check if any of the packages are outdated. And basically, we measured how much time it takes. And on Debian level, it would take only 20 seconds to create one snapshot. So you can do it pretty frequently, once an hour, for example, or half an hour. And we also measured the bandwidth overhead on the client of this approach, and it was just 16%. Doesn't matter what repository size is. So just to conclude, CHAINIAC is a framework which tries to eliminate the single points of failure from release validation process. And we introduce Skipchain as a data structure, and we use it for efficient logging and secure key evolution in our paper, but we believe that it has much broader applications. For example, you could verify the professional certificates on a blockchain, basically assuming that someone comes to you and you have on a Genesis block, and you will be able to jump forward and see that this certificate is indeed in the history. And we believe it can be useful for cryptocurrencies because with multi-hops you can do verification of the payments much faster. And for example, for offline update verification. And if you're interested, you can go to this blog article and blog post and read an exciting story about Alice and Bob who verify each other with Skipchains. And we also introduce verified builds, which we believe a step forward or aside from reproducible builds, and because it brings reproducible builds closer to end users and makes it more feasible. And finally, if you read the paper, you will find more information. For example, role-based architecture, which is probably the solution to go for big companies. And the multi-package CHAINIAC is basically what I mentioned, how to secure big distribution. And that's all. Thank you, and I'm happy to take your questions.
We have time for a couple of questions. Okay, I have a question. So one of the big sells of this work is that it could potentially be used in situations where you have a closed source setting, right? But one of the challenges you mentioned is that vendors would have to sign this NDA because presumably you could have like some IP issues, right? So have you talked to vendors about adopting this or?
Well, we haven't talked yet. But for us, the first adopter would be Debian, because we've already done all the experiments, and it's not closed source. But just an example of Microsoft, who reveals the source code of Windows to the partners by signing NDA. So I don't think it should be a problem, unless it's some army secret documents, something like this.
So great work, great talk. So I had a question regarding the use of blockchain, specifically, I guess you're using BFT-COSI for the authority signatures.
Yeah, we use BFT-COSI specifically for key evolution, because we want a consensus among the authority members about the new set of keys.
Right. So the question would be, let's say we live in a world where we did not have that, and you wanted to still get most of the benefits of what you've done in this work, together with the verified builds and so on. Do you think it would be possible, and do you think what would you lose in terms of, say, features and security in that aspect. So essentially the question is, if there were no blockchains, what would you lose?
So for example, in the release transparency log, the skip chain is not really used. It's just a hash chain with all information included. So it would be critical. So the critical part is actually to have it available to the users. And the main benefit of skip chains, for example, is that you can actually do offline verification. Because you take an update, for example, from an untrusted person or organization, and the person would give you links from the blogs that you have, and you would be able to verify that it's a valid release.
Thank you. So just to make sure that I understand correctly, you're saying in the case where you would not need offline verification, for instance, if you could go to each of the servers individually and verify that they have the same view that you have, basically, then you would not necessarily...
if you could go to all the CAF40 members, assume you have 100, and ask them all if they have the same view, it would provide about the same guarantees.
Absolutely.
So, and just
thank you.
Skip chain is a more efficient way for that.
Yeah, no, but you can still use skip chains in that setting, right?
Yeah, that's true. Yeah.
Yeah. Thank you.
Thanks for the question.
Okay, let's thank the speaker again.